It was quite a long time ago to have a lecture last time. So let's briefly review what we learned last time. Let's see. Yeah, so this matrix, different perspectives of understanding matrix multiplication. This is really important, and I think I sent you some video link that describes this this different perspectives of matrix multiplication. Did I or not? Okay, yeah. Maybe then, I'll send those the video links. Where you can study 4 different perspectives of this matrix multiplication. But during the last class, I think we explained most of them. And so, the main point here is that there are 4 different perspectives, and the main one, probably the most important one, is to view this matrix vector multiplication as a column combination, right? So if we have a matrix and the vector on the right as a product, and then we have a column vector here, and then we have some scalar which work as a linear combination coefficient associated with these columns, right? And so that way we view it as a column combination where the columns are provided on the left matrix and the linear combination weights are provided on the right vector, right? And thus, in this case, we can see, we can understand easily that whatever the coefficients are given, the resulting vector, this matrix vector multiplication will produce a vector, and that vector will always be inside of the span of those column vectors. And so the definition of the span is all the possible linear combinations of the given vectors, given column vectors, right? So given whatever linear combination coefficients that are given on the right, so this result of matrix vector multiplication will always give you the vector existing inside of the span of the given vectors, right? So that way, if we have this form of a matrix vector multiplication, so we have 2 vectors in 3-dimensional space, right? So given whatever 2 vectors that we have in 3-dimensional space, there all the possible linear combination of these 2 vectors will be just a thin plane, and so the resulting vector will always be inside of that plane, so it cannot go beyond, or the resulting vector cannot be produced or generated outside of this thin plane, right? Okay. Okay, and then this inverse of a matrix defines only for the square matrix, right? So in the case of a rectangular matrix, so we cannot talk about the inverse, okay? Because inverse, whether the matrix is invertible or not is only, can be only discussed for the square matrix. And also, so the last time we discussed about the following things. So the definition of the inverse matrix is that the inverse matrix denoted as this a to the power of -1 should satisfy this equation, right? So it means this should be identity, and also this also should be identity, right? So we have to satisfy these two equations, right? But in practice or in reality, we can only find the matrix that satisfies only one of them. In the case of our matrix is a square matrix, right? So in the case of square matrix, that's when we can discuss whether that matrix is invertible or not. And if you found the matrix that satisfies this equation of a times a to the -1 or a inverse is equal to identity, and then the second equation is automatically satisfied, right? So even though we haven't proved it, but that's always true for the square matrix, okay? And so in this case, some student asked the question about how we compute this Gaussian elimination. That actually is the algorithm to compute or obtain the inverse matrix. Okay, so even though the explanation was brief, but having that at a high level in your mind, so I strongly encourage you to review or study how to perform this Gaussian elimination. And I'm also considering, for our midterm exam, even though we didn't have many classes before our midterm, but we plan to have a midterm exam, because having no exams means you guys don't study or spend time on this class, right? So without spending much time on this class to review the class, then it will give you no no knowledge or the background on this class. So in order to give you much background or have a chance to study this class, so we will have a midterm exam. And so the midterm exam scope will be the ones that we discussed in this class, of course. And at the same time, it will cover some of these undergraduate level linear algebra knowledge and and the computations. So I will give you the detailed list about those topics, but certainly this Gaussian elimination will be one of the topics that we will cover. Okay, so I hope you can utilize this opportunity to review your basic knowledge about the undergrad level of linear algebra. And the exam date will be it will be in this in 2 weeks, right? 24th of October. So that will be our exam date, and it will start from 10:30. Just as your usual 4-hour class. Okay, then let's see. Okay, related to this property or this definition of the inverse matrix, I mentioned that satisfying one of them will automatically guarantee that the second one is satisfied or holds true for the square matrix, right? So, but what about the rectangular matrix? So, even though the rectangular matrix doesn't have an inverse at all, it doesn't even make sense to discuss whether a rectangular matrix is invertible or not, right? Because the definition of the inverse matrix is only applicable to the square matrix. But just purely looking at this equation, can we try to find the matrix that satisfies this equation for the rectangular matrix? Okay, so even talking about the before talking about the inverse matrix at all, just purely looking at this equation, and then we want to identify whether we can find some matrix, given some rectangular matrix. So can we find this guy, matrix B, that satisfies this A times B equals identity? Or can we find this? Okay. So as our conclusion, even though we don't prove it in detail, but in the case of rectangular matrix, you have a possibility. For some matrix, you can find this matrix B that satisfies this, or you can find some other matrix C that satisfies this, but not both of them. Okay, so so in some cases, in some rectangular matrix, you cannot find any matrix that satisfies this or this. So that means, so there exists, there doesn't exist any matrix that satisfies this equation or this equation. Okay, and also some other cases correspond to the case that you can find the matrix B that satisfies the first equation, but not on the second equation. So once you found the matrix that satisfies either of them, and then you cannot find the matrix that satisfies the other one. Okay, so that is the property for the rectangular matrix. Of course, rectangular matrix also includes the square matrix, right? So we exclude. So in this discussion, we exclude the case of really square matrix, but we discuss about the non-square matrix. So again, in the case of non-square matrix, you have a possibility of finding one matrix that satisfies one of these equations, but that means the other equations cannot be satisfied for any given matrix. So you shouldn't be able to find the matrix that satisfies the other equation. And also, in the case of the matrix A having the size of maybe 5 by 3, and then what should be the matrix size of B? And I as well. So the first number should be, of course, 3, right? But what about the second number? So it should be 5, because even though A or B can be rectangular matrix, but our identity matrix that should satisfy this equation, that is involved in this equation, should be square matrix. So there is no rectangular identity matrix, right? So identity matrix should always be square matrix, right? And so what about the size of this identity matrix? So these two are the middle number, and so the resulting matrix size will have this number of rows and this number of columns, right? And so we cannot change this number, and so we have to make this number equal to 5, right? So 3 by 5 should be our matrix B, which has the size of the A transpose. Transpose version of the matrix A, right? And so in this case, we can write it as I5, just indicating it is identity matrix with the size of 5 by 5, but it is always the square matrix, so we often just write this as I5. And then what about this? In this case, it is 5 by 3, and so C should be also 3 by 5, right? And so in this case, the identity matrix should have the size of a I3, right? Okay, so in this case, so we have the first and the second equation. So again, I mentioned that for some matrix A, yeah, so we still consider the matrix size of a 5 by 3, okay, and I mentioned that those two equations cannot be satisfied. I mean, at all. Either equations cannot be satisfied, but sometimes one of them can at least one of them can be satisfied. So, which one has the possibility of being satisfied? The first one and the second one. So it is related to a rank thing. So in the case of 5 by 3 matrix, what is the maximum rank? Is it 5 or 3? So we have this property, right? So the matrix rank is less than or equal to the minimum value between m and n when the matrix size A is m by n. Okay. You guys know that? Okay, so I'm not sure if I can do like quick proof, but yeah, okay, so maybe then it will be our homework for you guys and also for me. Okay, so let's find out the the proof about it. So you guys know the definition of the rank, right? I think we discussed it briefly last time. What is the definition of the rank? What is the definition of the rank? Right. Right. So it is like dimension of column space of A, right? So what is the column space? It is span of columns of A, right? So in this case, so we have 3 columns in 5-dimensional space, right? So this is our matrix A. So the dimension of this column space. And so if we so even though we have a even if we have 3 columns in our matrix A, it does not mean that our dimension of our column space is 3, right? So it may be smaller or equal to 3, smaller than or equal to 3, right? In case it is smaller than 3, and then it means we have linearly dependent columns, right? So let's just consider like a 4-dimensional space for this column vectors that we have in our matrix, and 1, 2, 3, 4, and 5, 6, 7, 5, 6, 7, 8. So these two, so you can, you intuitively, those linearly dependent or independent columns, you can think of this as follows. So we gradually, add one vector at a time. I mean, one by one. So the first vector is like 1, 2, 3, 4. That has a specific direction. And then what is the span of this single vector? It will be just a line which contains all the linear combinations. And then let's just add the second vector. The second vector is added, and if it is pointing to different direction from the first one, and then this is when it spans, it increases the span of these two vectors, right? So in that case, the span of these two will be increased to plane from a line, right? And then we keep adding one vector at a time for these all the given column vectors in our matrix. And then suppose we added the third vector, right? And then now in this case, that where this third vector is pointing to different directions that are not covered by these two, and in that case, the span will be increased into 3-dimensional space, right? But what if our vector, third vector is inside of the span of these two, right? So that's when this third vector is represented as a linear combination. It is already represented as a linear combination of the previous two. That's the meaning of this vector being inside of the span of these two, right? And so in that case, this vector, when adding the third vector, it didn't increase our span of these three vectors, right? So this is the linearly dependent case, right? So given these multiple vectors, we just keep adding one vector at a time, and then we can identify for each vector whether that vector increases our span or it doesn't increase. Okay, so if it doesn't increase, and then we have to remove it as our basis, right? So so if we have like 5 different columns, and then we still think of scenario where we add one vector at a time, and then if it actually increases the span, and then let's just denote it as I, which means this vector is a linearly independent from the previous vector. And so I and D, which means the third vector is already represented as a linear combination of the previous two, right? And then I and maybe D. So in this case, what will be our number of bases or the dimensions? It is 3, right? So the actual linearly independent basis vectors will be these 3, right? And so the dimension will be 3, right? So so in this case, certainly the rank, the rank has this rank of a matrix is just nothing but, that is literally defined as the dimension of the column space of an A, right? And so in this case, the rank will be 3. So we can easily see that the rank, the maximum rank value will be the number of columns, right? Right. And then what about this? So 5 by 3, and then we have a 3 columns, right? So the maximum possible rank value will be 3, right? But why should the rank be also confined, restricted to be smaller than this m, or the number of rows? Okay, so I'm doing the proof about it at an intuitive level already, but so in the case of this, what was that? 5 by 3 matrix, and then the minimum value between them will be 3, right? So in this case, we don't need to consider the number of rows, right? But let's just consider the case where we have just see, we have a smaller number of rows than the columns. For example, 3 by 5. And in this case, we have 5 vectors, right? But what about their dimensions, where these vectors are living in? So it is 3-dimensional vectors, right? So in that case, our entire space, so we can think of the basis of the biggest possible space in this 3-dimensional space. So these vectors are living in the 3-dimensional space, right? And so even if we consider the biggest possible space of this entire 3-dimensional space, the basis for this entire space will be 3, right? And so it cannot be more than 3, right? So in this case, would it be possible? It is not, because we added the first vector and the second vector that still increases our span, and the third vector was included in the span of the previous 2, and then fourth vector increased the span, right? So up to this point, our dimension of this column space by just considering the first 4 vectors. So that the dimension of that subspace has already reached the maximum possible dimension of this entire space, of 3-dimensional space, right? And so that means, yes, like 1 to 4, maybe 2, 1, 3, and then 1, -1, and -1. I just subtracted the first one from the second one, so that the third one is a linearly dependent, of the previous 2. So in that case, this one is a linearly dependent one. And then let's say 3, 4, 5. Yeah, I haven't checked whether this guy is really the linearly independent of the previous 2, but likely, I think it's likely that this guy will be linearly independent. And so, once we found the 3 linearly independent vectors in 3-dimensional space, and then it means the span of these 3 linearly independent vectors will entirely cover the whole 3-dimensional space, right? And so after this point, whatever vector we add to our kind of potential basis, it will not increase the subspace dimension, right? Because there is no room to increase. Okay, so should be D. Okay, so that way, our rank or the dimension of this column space will always be restricted to this number of rows and most. Okay. Any questions about it? Okay, and then back to the question that I asked about which one has the possibility of being true between the 2. In this particular case of 5 by 3. So let's do some poll. The first one, the second one. Again, the first one, this guy, or the second one. Okay, so you guys have no idea, right? Almost no guys raised the hand. So this one has only this guy, or the second guy, has the possibility, but not on the not the first one. I mean, there is no chance, or it is impossible that the second one, this first one is satisfied in this particular case. and it is related to the number of pivots, or maybe the rank, or so. Yeah, suppose we have this kind of pattern of I independent, independent, and dependent, independent, and dependent for this 3x5 matrix. And then we can think of some elementary row operation or Gaussian elimination applied to this matrix. Okay, so in that case, so we will have like this matrix, and then we will do the row operation, and then the row operation. So there are 3 different row operations, right? So what are these 3? So the easiest one would be row interchanges. Row interchanges. Okay, let's see. Okay, let's think of this case, and then how do we represent it as a matrix? It's, we first construct the augmented matrix. So the rightmost column is corresponding to the values, I mean constant values given on the right hand side, and the left part is just collection of our coefficient matrix, right? And so the Gaussian elimination is the process of solving this equation by using variable elimination, or in Korean 가감법으로 이거를 푸는 과정이라고 했죠. 네, 근데 but we follow specific rule consistently, and that rule is to remove the first variable. Yeah, right? Remove the first variable by using the first equation. We remove the first variable in the subsequent equations, right? And so that's the effect of reducing the problem size, by just excluding one equation and one variable, and thus we started from 3 equations and the two unknowns, and then we can now exclude the first equation after using it to remove this part in the subsequent equation, and then we end up with one less number of equations, like 2 equations and 1 unknowns, right? So that's how we do this Gaussian elimination, right? And so here, we do the there are 3 types of row operations that we can do during our Gaussian elimination. And so the first one, I mean, there is no really order, and one operation that we can do is to just freely switch the order between the equations, right? So we can interchange it between the rows, right? So when do we use it? So that is needed when we have 0 over here. So we have 0 here. So in this case, we have to use this guy to remove those 2, right? By just multiplying the first equations, right? And then subtracting it from each of the subsequent equations, right? But if it is a 0, right? And then in that case, it cannot be used as an eraser, right? And so in that case, if it is 0, and then we look at the lower equations and find out, pick up the first appearing equations that has non-zero coefficient for that corresponding variable, right? So if it was 0 and 0 and 2, and then we will pick up this guy by just scanning from the top to bottom, And then this is the first equation that has the non-zero coefficient on that first variable, and thus we switch between these two, right? And so that has the effect of changing between the two equations, and when solving this set of equations, the order doesn't matter, right? So these are just a set which is an unordered list of equations, right? So we can freely change it, change the order, and so that is corresponding to interchanging between the rows. And then what about the second one? I mean, the second one is just a scaling of single equations, right? So okay, let's just actually do some Gaussian elimination, like 2, 1, 3, and then so we have to multiply 1/2 by 1/2 the first equation, and then subtract it from the second equation, right? And then what about these number? This number should be 0. And then what about this guy? .5, I think, right? And then it is 2.5, right? So that is the resulting, I mean, second equation after doing the one step of Gaussian elimination by, I mean, after removing this variable, right? You guys are following this, right? 이거 이해가죠? What about the last row? We just multiply 1 by 1 and then subtract it. So 0, 3, 3, right? Okay, and so we use the first equation as an eraser. And so that is done for its row. And so we have all zeros, right? And then from here, we use this guy as an eraser as well, right? So once we erase it by just multiplying it by 3 over 2.5 and then subtracting it, and then it will be 0 and 0, right? Okay, and so even though we have 3 equations, the last equation has no effect after doing this elimination, because the last equation just became 0 times x plus 0 times y equals 0, right? So that has no effect, right? And then now we go back, and then we now do the backward elimination, as you recall, or as you guys remember this process. And then, yeah, we pick up the last variable from the last equation. And then now we do the similar thing of removing the variables from the upper equations, right? And so we use this as our eraser, and then make this guy as 0, right? But before doing it, we have an option to make it simple, so that this guy is multiplied by 1 over 2.5. So that means, I mean, in the case of second equation, it means 2.5 y equals 2.5, right? And so let's just divide this equation by 2.5, and then it will be 1 times y, right? 1 times y equals maybe 1. And so yeah, we can just scale a single equation by a certain factor, okay? And then we can always make this as 1, and then yeah, this value happened to be 1, right? But that just follows after this through this scaling of a single equation. So that is the second operation. So the first one is the interchange, and the second one is scaling of the single equation, and then the last one is what we already did when changing the second and the third equation, which is like row replacement operation, replacing the each of the subsequent row right? By just subtracting the multiple of the previous or the other equation, right? So that is called the row replacement operation. So that is the third operation. So from here, we multiply this by 1/2 and then subtracted it from the second equation and then replaced the result, the second equation with the resulting equation, right? So that way we basically replace the second equation, right? So that is called the row replacement. Okay? So we have these three different operations: row interchanges, and the single row scaling, and row replacement by subtracting the multiple of the other equations. Okay. Okay, and then once we do this Gaussian elimination, and then it reveals something called the pivot in this matrix, and so this pivot, yeah. So in this case, yeah. Once we do the row scaling on this, and then it changes 0, 1, 1, and then we remove this guy by using this, right? And so we subtract the second one from the first one, right? And so the first one is 2 and 0 and 3 and 0, 1, 1, 0, 0, 0, right? And then we can also scale this guy as 1. Oops, it should have been 2, right? And then it should be 1, right? Okay, so this is the final result of Gaussian elimination on this matrix, right? And then what are the pivots in this case? Pivots are those numbers. So what is the definition of the pivots? So the pivot is the leading entry, which is the first appearing non-zero term, non-zero value from the left. Okay, when starting from the left, the first appearing non-zero entry in the row, but those rows should be considered for this Gaussian elimination result. Okay, so leading entry, I mean the definition of the leading entry is the first appearing non-zero entry at a given column. Okay, so for example, like let's think of this matrix. This. So what are the leading entry? Leading entry for the first column, I mean the first row. So leading entry is considered as a row, for row, and the 1 is a leading entry 3, and the 4 are the leading entry, right? But after we make this matrix into Gaussian elimination form, I mean the result of the Gaussian elimination, and then that matrix is also having a name of reduced echelon form. I mean, there are many different, many terms that are introduced, but actually they are all, studied. I mean, all, discussed in the undergraduate level linear algebra. So, once we obtain the Gaussian elimination result, and then we consider this leading entry, which is the first appearing term in every row, right? So those leading entry are called pivots. Okay, pivot. So again, you first make the Gaussian elimination result, and then you find the leading entry from that matrix. Those are called the pivot. Okay. So here, this is the result of our Gaussian elimination, and so the first column has 1 here. I mean the first row, sorry, has 1 here, and the second row has 1. The first leading entry over here. And what about the third row? So it doesn't have any non-zero value. So it doesn't have any pivots or any leading entry at all, right? And so we now find the two pivots, right? Two pivots, the first one and the second. Okay, and so in this case, this pivot, okay, these pivots are actually telling you whether this column is linearly independent or dependent of the previous column. Okay. So we have a leading entry over here, and so even though the leading entries are obtained for each row, right? And then once we obtained those, all the leading entries, and then we can now consider the columns of a matrix. Okay. So again, we found the leading entry by just picking up the first non-zero entry at each row, and then once we found all the pivots, and then we consider column-wise. I mean, whether this first column has the pivot, or the second column has the pivot, or the third column has the pivot. Okay. So if this first column has the pivot, and then it means this column is linearly independent one. When we keep adding one vector at a time and decide whether that is a linearly independent of the other, I mean of the previous one, okay? So that is actually the same as this, whether this column has the pivot somewhere in the three different rows. Okay? So basically those two columns are having pivots, right? And so those are the linearly independent ones. But what about the third one? Third one doesn't have any pivot, right? So that is when that means this, when adding the first and the second and the third row columns, and then this guy doesn't increase our span, which means that this guy is linearly independent of these two. Okay, and so yeah, back to the original point. This matrix was originally coming out of this set of an equations, right? So this set of an equation, we just apply the Gaussian elimination, just try to solve or obtain the solution for this this set of an equation. But this row reduction or this Gaussian elimination is actually directly related to whether each column is linearly independent or dependent. Okay, so yeah, let's check this kind of result from purely looking at the columns of this matrix. So here we have 2, 1, 2, and 1, 3, 4, and 3, 4, 6. Okay. So can we find so it means the third column didn't have any pivot in the result of Gaussian elimination. That means it is linearly dependent of the previous two, and thus the third one should be linearly, represented as a linear combination of the previous two, right? And so let's try to find the coefficient. Yeah, we can just simply find the coefficient, by just eyeballing it. So we just use the linear combination as weight as 1 and 1, right? And then we obtain the third one. And thus, when adding the first one and the second one and the third one, and then the third one will not increase the span of our column space, right? And then, let me also discuss another thing. So in this, this is the result of Gaussian elimination, and the result of Gaussian elimination has the name called reduced echelon form. Okay, reduced echelon form. Yeah, but you guys don't need to remember the exact, the specific name about it. But okay, so in this case, let me ask this this question. So pivot is counted. Pivot is chosen from each row. Then is it possible that, for each column, for some column, is it possible that we have more than one pivot or more than one leading entry? So it is not actually. So in general, the leading entry can be found, multiple leading entries can be found in the single column. So for example, 1, 2, 4. So in this case, what are the leading entries? So the leading entries are these, right? And so the first column certainly have 2 leading entries, right? So that's certainly possible for general matrices, right? But when considering those leading entries from the result of the Gaussian elimination process, and then each column will have at most 1 leading entry or at most 1 pivot, right? Or it can have no pivot at all, like this case. Okay. So that is because. So why is it so? How can we understand? Or how can we admit that each column should have at most 1 leading entry? Can anyone give a kind of logical explanations? By just
that column eliminated by the quotient elimination.
Yeah, right. That's right. That is right. Yeah. Yeah. So from this process, so we pick up the non-zero coefficient, right, from the topmost equation. I'm just describing again the Gaussian elimination, and then we remove all the non-zero values in the corresponding column in the subsequent or lower equations or lower part of that column, right? And then we do this Gaussian eliminations in this fourth phase, right? And then we pick up the rightmost one, rightmost and the bottom one, and then we now do this elimination process of removing non-zero entries on the upper part in the same column, right? So once we found one non-leading entry, and then in the fourth phase, we make all the lower part within the same column as 0, and then during the backward phase, by using that non-zero one, we now look at the upper part within the same column, and then make all of them as 0, right? And thus, we end up with at most 1. Only 1 non-zero entry within that column. So does it make sense? Okay, so I think I briefly mentioned about the process of computing or obtaining the inverse matrix. So how do you compute the inverse matrix of 1, 2, 3, 4, 5, 6, 7, 8? So if it is 9, and then it is not invertible, I think. It's probably. So let's make it as 10, which is one example of an inverse matrix, I believe. So how do we obtain the inverse matrix of this? So we basically do the Gaussian elimination on this matrix, even though this is not a set of an equation. This is not a matrix representation from the set of equation that we are initially given. So yeah, so starting point in the case of solving the linear systems is that we are given the set of equations, and then we represent it as this matrix, and then apply the Gaussian elimination, right? And then that's the equivalent process of solving the solution, right? But let's just think of the situation where we just are given this matrix, and then try to obtain the inverse matrix of it. Okay, so in this case, so that is the process of like AX equals identity matrix, where A will be our inverse matrix, right? Then so this kind of thing can be viewed as this guy: 2, 1, 1, 3, and 2, 4, and xy 3, 4, 6. Right. So this is called the matrix equation form of a linear system, right? So can you understand this? So initially we were given each equation's row-wise. Each equation is represented as each row, right? But as a whole set of these multiple equations, and then it can be rearranged into one single equation. I mean, yeah, again, one single equation where we have matrix on the left and the variable vector on the right, and then the resulting vector on the right is just the coefficient matrix, right? So you can easily verify that, right? So this guy times this, the inner product should be the same as 3, and so on, right? And also by applying the column combination perspective, and then now we can understand these two, okay, these two columns and their column combinations by using the linear combination coefficient of an x and y. That should produce the resulting vector 3, 4, 6, right? 3, 4, 6. And so here, yeah. So in this case, suppose this given matrix given vector on the right. Suppose this guy is outside of the span of these two column vectors given on the right. So that means this guy is the outside of the span of these two. So 2, 1, 2, 1, 3, 4 is spanning some plane, right? And then suppose this 3, 4, 6 is another vector that is actually outside of this plane. Okay, and then it means that vector, cannot be linearly, cannot be represented as a linear combination of the previous two, right? So in that case, we have no solution at all, right? But that is, if that is an inside of this plane, and then that's when we have the solution, right? Which means this guy can be represented as a linear combination of these two, right? And so, so this is another kind of review point, which we studied in the previous, the undergraduate level linear algebra. But so here, what is the IID kind of a pattern here? So here, it has the pivot and no pivots, right? So it means the last column, which corresponds to this guy, 3, 4, 6, is represented as a linear combination of the previous two, which means the last guy doesn't increase the span, right? And that's when we can find the solution. But on the other hand, the last column happens to be outside of the span of the previous two. Then that's when we have no solution at all, right? And thus we can we can understand the point that if we find the pivot on the last column, then that's when we have no solution for our linear system. So does it make sense? So again, back to this. We just aggregate or concatenate those two and that rightmost column into one single matrix, right? And then it actually doesn't matter among these columns whether a particular column is increasing our span or not. There are maybe i's or d's within those column vectors, right? But this guy should always be D or linearly dependent of the previous ones, so that we can have the solution, right? Okay, and let me point out, one more thing. In this case. So, so here, what is the meaning of being able to find the solution? I mean, what is the meaning of the fact that solution exists? That is, the linear combination coefficient x and y exists. That satisfies this equation, right? But this guy, okay, this reduced echelon form, which is the result of the Gaussian elimination. So it is certainly different matrix from the original matrix that we started with in the Gaussian elimination, right? So how is it related to the solution for this original matrix equation, or the matrix defined as these numbers, but after doing the Gaussian elimination, we certainly obtained a completely different matrix, right? What's the relation between them? So all the transformation of row interchanges or row scaling or row replacement. So those three operations that we did in the Gaussian elimination, that is guaranteed to, not to change the solution for this, right? So, what is the process of solving this equation? So, by using these two, we can just maybe multiply the first one by half and then subtract it from the second one. Let's just forget about the Gaussian elimination and then let's just try to solve this equation, and then the resulting equation will be 2.5 times y equals 2.5, right? So we obtain y equals 1, right? So how do we guarantee that this guy is the solution for this? That sounds really obvious, but the reason why the solution for this is actually the solution of this original system is because our row operation is not changing the solution at all, right? So whether we interchange between the rows, that guarantees not to change the solution, and we just scale some single equation, and that also guarantees not to change the solution. And also row replacement will also guarantee the solution to stay the same, right? And so this matrix and their corresponding linear system, it is like 1 times x plus 0 times y equals 1, and 0 times x plus 1 times y equals 1, and 0 times x plus 0 times y equals 0, right? So this is the converted form into set of equations that correspond to this matrix form that collects the coefficient and the rightmost column, right? So this equation has the same solution as the initial set of equations, because we only apply the steps or processes that doesn't change the solution at all, right? So in this case, it can still be viewed as like 1, 0, 0, and 0, 1, 0, and 1, 1, 0, right? Sorry. Sorry for getting messy here, but as x and y and 1, 1, 0, right? So we can represent these set of equations into that single matrix equation, right? So the solution for this and the solution for that, and also the solution for this and solution for that, all the 4 different cases will share the same solution. And that means in this particular case, so we have 2 different column vectors, and then we have to find out some suitable linear combination coefficient that will produce this vector. And then suppose we found the linear combination coefficient that satisfies this by using those two columns to produce that one. And that linear combination coefficient of an x and y is actually the solution for this equation. So this equation is also trying to find out the linear combination between 1, 0, 0 and 0, 1, 0. So those two columns are certainly different from the like this 2, 1, 2 and 1, 3, 4, right? So it's a certainly different set of columns. And the B part, 1, 1, 0, is also different from this 3, 4, 6, right? So we are dealing with a completely different set of vectors, right? But still, the solutions guaranteed to be the same, right? So the linear combinations that will make this equation hold true, that will also make this equation hold true. So the linear combination coefficient should be the same, right? Any questions? Okay, and then yeah, so I have some more to say about the relations between this solving the linear system through Gaussian elimination with the process of, with the ways to compute the inner product matrix. Inverse matrix. Okay, so the inverse matrix like this. So yeah, this guy is done through this Gaussian eliminations with in the same manner. But let's continue to after having the break until maybe 12. Yeah, so yeah, let's start at noon.
저랑 같은 연구실인데 친구 한 명이 다음 주에 캐나다로 출장 가게 돼가지고
이거를 저기 그 강의 그 영상을요 녹화를 해갖고 올릴 테니까 네, 그 수업 때 꼭 그뭐 올 꼭 와야 될 건 없고요. 왜냐면 따로 엑스트라 타임을 잡아서 이제 하는 거라서 좀 나중에 영상을 보면 돼요.
퀴즈도 다음 주에
그렇죠. 그쪽으로 다음번에 와서 보도록 하죠. 네.
그냥 징빙이나 그런 거
징빙이요?
준비할 필요 없어요.
네. 그렇지만 예, 안녕하세요. 예. 호랑이요.
Really quiet. 50만 원 벌었어. 그러니까
너는
국수니까.
이러고 막
안 먹었어. 많이 하는 거. 왜 이렇게 티를 내려 그래? 본인이 뭘 하는지 그렇게 티 내고 싶어?
너 혼자서 간다.
정말 생각에 의식에 들은 게 어떻게 들어간지 궁금하다 이거 진짜.
정말 여기서 또 RPM 할때 채널 개수가 256이면 픽처 맵을 256개 쓰겠다. 근데 이 D 256이라 그냥 256개 필터를 쓰겠다. 그런 거지.
근데 사실 내 연립 방정식을 푸는 방법은 해석을 하는 거는 XY 값이 구하는 거는 걔를 갖고 이제 그 매트리스가 차지하는 공간에 대한 거에 집중을 하는 거지. 그러니까 가우시안 엘리미네이션이 여기서 붙이는 게 아니라 이거 가지고 역행을 해요. 그래서 그 다음 시간에는 설명해 준다는 게 역행력과 있는 건데 그래서 일단 가우시안 엘리미네이션이랑 피부를 설명하고 그 다음에 이제 역행력을 구하는 방법에 대해서
우리가 그냥 단순하게 이렇게
가우시안 엘리미네이션 A 우리가 보는 역행력은 그러니까 디터미넌트를 줘야 돼. 디터미넌트를 구하는 게 어려우니까 디터미넌트가 결국에는 피봇의 곱이 디터미넌트 나중에 어쨌든 그러려면 피봇을 구해야 되고 디터미넌트를 구하려면 나 집에서 운동하고 있으면 이렇게 있잖아. 그러면 여기 올라. 백분이. 언니 사는 거 같이 하는 게 아니라.
같이
알면 이렇게. 잘못했다고 이런 거 지금 하면 와가지고 내 얼굴 봐. 아니면 요가 매트를 하고 있으면 요가 매트에서 좀 싸우고. 운동 되게. 하면서 내 머리카락이 무너지다 머리카락 씻고 막 그러면
세상은 운동하는 제답을 못 들어.
모든 줄 알았어.
멘붕 왔어. 정말 더 안 쉬고. 정말 잘 먹었다. 생각보다 곳곳에 계시더라고요. 그리고
초등학생 학생 설명회 때
네. 어디 있나요? 뭐 무슨 회사님?
잘못 봤는데. 이제 많이 아홉 시에 왔어. 게임 얼마나 하려고 게임을 하게 되는
신경 없어. 이거는 몇 시면
All right, let's continue. Okay, so in terms of an overview of what we are currently studying, so we reviewed Gaussian elimination and their meanings in terms of this matrix equation. So this is called the matrix equation, or this guy, because this is a equation that involves a matrix, right? And so also we studied about the corresponding pattern between the existence of a pivot. I mean the columns having a pivots are actually corresponding to the columns that has the that is linearly independent of the previous columns. Okay, and then now, and also we just discussed that this Gaussian elimination process. I mean this entire process don't change the solution at all, right? And thus the resulting matrix of this Gaussian elimination that has the same solution as the original equations. Okay, and then now we discuss about this the process of computing the inverse matrix through this Gaussian elimination. Okay, so how can we compute this inverse matrix X? So of course, if we have a 2 by 2 matrix of 1, 2, 3, 4, and then we know the Gaussian, the formula for computing the inverse matrix of this, right? How? AD minus BC, 1 over AD minus BC, and DA negative B negative C, right? So that's the formula that we are familiar with. But for 3 by 3 or larger matrices, it is difficult to come up with the formula. Although we can build up the formula, but it is in general really complicated. That has no convenient way to memorize it. Okay, and so in general, computation of the inverse matrix is through this Gaussian elimination. Okay, and then the Gaussian elimination is as the formulation or the problem is set as follows. So suppose we are given this matrix and then we want to compute this inverse matrix, and then we want to be able to find this matrix X when multiplied on the right, it produces the identity matrix, right? And we know if A is 3 by 3 and X is also 3 by 3, and also I is a 3 by 3. Okay, and then let's so X is identity and this, right? And then so this entire matrix for X is our unknown, right? And then let's call it as X, Y, and Z. Okay, so in this case, so we do not know yet about those values. So let's just ignore for now those second and the third column on the matrix X. And then we have X, Y, and Z, which is our first column of X. And we have matrix over here and multiplied with the first column. And then that will produce what? The first column in the resulting matrix, right? Because so doing the inner product will produce this guy and this guy, this guy, and this, right? Okay, so the first column of the matrix X, which is on the right, okay, that will produce the first column of the resulting matrix. Okay, so the point is these variables in the first column will only be related to the first column on the right. I mean, on the right hand side, right? Okay, so in this case, if we generalize this, and then we can actually decompose this guy, which is a matrix and the matrix, and also, I mean, where our matrix, I mean, our variable is also a matrix, and that seems to be quite complicated, but that can be just independently decomposed into three different linear systems, or three different set of equations. And how? Yeah, we have the same matrix A and XYZ that is equal to 1, 0, 0, and A times WVU will be producing the second column in our identity matrix, right? So yeah, it is decomposed into three pieces of, I mean, three sets of linear equations, right? So we can just solve them independent, right? And then how can we solve this? How can we solve this? So we just build up our augmented matrix, right? Just like this, right? And then do the Gaussian elimination, and then that's how we can obtain the solution, right? So if we can find, yeah, if we can find the solution for this matrix, and then now at least we can fill out the first column of matrix X. And if we can fill out each of these three columns of an X, and then we now completed our inverse matrix of an A, right? So that means, yeah, we found the solution over here, the solution over here, and then the third one, and if we found the solution, and then collecting them into one single matrix, and then that will give you the final solution for the inverse matrix, okay? So that's how you can find the inverse matrix. Okay? Then, yeah, I don't have an, yeah, I cannot think of an easy way to prove, but this 1, 0, 0, 1, 0, 0 will be evolved or change it through our Gaussian elimination. So yeah, so what I mean by that is 1, 2, 3, 4, 5, 6, 7, 8, 10 in order to make it likely invariable, and 1, 0, 0, that will be our augmented matrix, and we'll do the Gaussian elimination, right? And then let's just imagine the final result of the Gaussian elimination, and then it will, suppose it is like 1, 1, 1, okay? And 0, 0, 0, 0, 0. And this 1, 0, 0 will be changed into some vector, right, through this Gaussian elimination. Okay, and then now for this guy, when starting with the 0, 1, 0, in that case it will be transformed into another vector, right? Okay, and then in the case of Gaussian elimination, so you guys can easily find that, I mean, regardless of this part, okay, this part, yeah, this part, that corresponds to the coefficient values, okay? That part will always be, will be the same, okay? Will be the same regardless of those B vectors, right? So if you imagine it, using this guy, we will remove this guy, right? And then from here, we will use to remove this guy, right? And then we may have a non-zero over here, and then we now look at the upper part, and then we remove these two, and then yeah, we remove this, and so on. So this will be like a rough overview of the Gaussian elimination And through this process, yeah, this last column will just follow, and that is not actually playing a major role or like really meaningful. That doesn't play a meaningful role to control what particular Gaussian elimination step to apply, right? Because in this process, the forward process is all done by using this guy and this guy, and then remove this, and then remove this, and remove this, right? And so this part, I mean, yeah, whatever vectors that we have on the right and the rightmost columns, that will have no effects. So yeah, my point is that this part is yeah, always the same. Okay, always the same. Okay, then yeah. So even though 1, 0, 0 and 0, 1, 0 and 0, 0, 1 is transformed in their own manner into another vectors, okay? But yes, so this is a little bit inaccurate part or logical jump, but suppose the resulting vector is somehow 1, 0, 0 and 0, 1, 0, 0, 0, 1. I mean, let's assume that these vectors didn't change at all. I mean, it is just a simple, simple case. I mean, just yeah, a little bit logically imperfect scenario, because it will be changed into really different vector. But let's just make the assumption that somehow these vectors didn't change at all and then stay the same. Okay, and in this case, I mean, I just want to discuss when we have no solution for one of these 3 equations at least. Okay, so if we can find the solution for all the 3 equations, and then that's when we can compute or we can obtain the inner product. Inverse matrix. But if we cannot find the solution at least for one of these 3 equations, and then that's when we can not find the solution. Okay, so in that case, suppose the last column was 1, 0, 0. Okay, so in this case, can we find the solution? I mean, the last column itself will be our solution, but let's just think of the column combination perspective, which means we have these 3 columns, 1, 0, 0, and 0, 1, 0, 0, 0, 1. And let's just produce 1, 0, 0 as a resulting linear combination of the 3 vectors. And certainly, yeah, we can just use the linear combination coefficient as 1 and 0 and 0, right? Because this guy has the non-zero value at the first dimension, right? And so we can easily obtain that yeah, linear combination coefficient. What about the 0 and 1? We can easily find that by using this pivot as well, right? Or that column, or 0, 0, 1. Okay, so in that case we can also find that particular column, that particular solution. So conclude, yeah. In conclusion, I mean, the main point that I want to make is in our matrix over here. So this part is corresponding to our matrix that we want to compute the inverse matrix from, right? And then this part, I mean, if that part has the pivot in every column, which means those 3 columns are all linearly independent when adding 1 vector at a time. Okay, if the 3 vectors are linearly independent and thus having a pivot at each column, and then that's when, yeah, we can find the solution for 1, 0, 0 case, and 0, 1, 0, 1, 0, and 0, 0, 1. Okay, so it's a really rough explanation, but yeah, we can guarantee to find the solution, okay, for all the 3 cases. Okay, so having a pivot in every column in our matrix after doing the Gaussian elimination So that is when you can find the inverse matrix. Okay. Okay, but let's just think of some other case where we have no pivot in some column. For example, we can find we can think of this kind of case. Okay, so suppose after doing the Gaussian elimination, we obtained pivots over here and over here, and no pivots anywhere else. So in this case, what's the meaning of this? So the first column and the second column is actually linearly dependent, which is the scalar multiple of the previous column, right? So that's why so it's like I D and I situation, right? Because we have no pivots on the second column, right? So in this case, we have no column. So in terms of like 1 0 0, we can fit, or we can generate this guy by using the linear combination by using this one, right? And then 0 1 0 can be obtained by using this column because we have 1 over here. But what about this guy? This guy, we cannot produce that 0 0 1 by using these three columns, right? Because we have no non-zero on the third dimension or third row, right? So it's like so we sometimes think of it column-wise. I mean, whether the column has a pivot or not. So in this case, we consider the square matrix because the inverse matrix is only considered for the square matrix, right? So square matrix means we have the same number of columns and rows, right? And so when some columns have when some columns are linearly dependent, and then it means we don't have a pivot in the corresponding column, and it means how many pivots do we have if we have a 3 by 3 matrix, and then the total number of pivots will be certainly smaller than 3. So here we have 2 pivots, which is strictly smaller than the number of columns, or 3, right? And that means we have the same number of rows as the number of columns, right? So what is the meaning of the rows? The row is each dimension of those column vectors, right? So the first dimension and the second and the third dimension, and so we have 3 dimensions, but we have only 2 non-zeros or 2 pivots, which means in among some of the dimensions we'll have completely 0, right? So again, each column will have at most 1 pivot, okay, which means we have a completely 0 columns, or we have a column where at most only one non-zero entry is found, right? So the number of pivots is the same, equal to or strictly less than the number of columns, right? And that the total number of ones are actually in this case the total number of ones or pivots are actually strictly smaller than the dimensions that where those vectors are living in, right? And so it means in some rows we can find the completely some rows should be completely 0, right? In the case of having strictly small number of pivots than the number of columns or rows. So in this case, so this is when we cannot find the inverse matrix in this case. Okay? Yep. So yeah, there are some other cases of having strictly less pivots than the number of columns. So the first one is IDI, or the second one is second case could be 1 1, like this kind of column. So in this case, I, and D, right? So in this case, yeah, we have we prepared for non-zero ones for the first and the second dimension, but the third dimension we have no non-zero entries that can fit or that can produce the linear combination for like 0, 0, 1 vectors. So, so in that case, we cannot find the inverse vector. Any questions so far?
일반 네트워크에서 만약에 레이어와 레이어 사이에 파라미터가 그냥 하이퍼 파라미터잖아요. 개수 정하는 거. 근데
네.
만약에 그런 개수가 뭐 정보를 찾을 수 있는 파라미터 개수보다 많이 만약에 설정을 모델 만든 사람이 설정을 했으면은 그러면은 그 W 레이어를 저렇게 매트릭스로 봤을 때 그러면은 저렇게 노는 그러니까 디펜던트한 애들이 많이 생기도록 학습이 되는 건가요? 그러니까 필요 없이 과하게 많아버리는.
네, 그러니까 뭐 기본적으로 여기가 3개고 여기가 뭐 5개다. 그러면 요 하나하나가 이 3개의 linearly independent, linear combination으로 표현이 되죠. 그러니까 예를 들면 여기가 so here when considering this fully connected layer where we have more number of node in the output layer than the number of input layer, the node in the input layer. In this case, suppose the coefficient is 1, 2, 3 and maybe 4, 5, 6 and so on. And then in this case, given the input vector, in the three-dimensional case, we have so this is the y equals wx, right? So here, so this is a 1, 2, 3 and 4, 5, 6 and 7, 8, 10 and so on. And then let's just consider the row, each rows, the first row and the second row and the third row and fourth and the fifth row. So in this case of I and D kind of patterns as a row-wise manner. And then suppose this guy is I, and maybe it is D and I and D and so on. So here in this case, we can generate only up to 3 linearly independent coefficients to produce each of our outputs, each of our 5 output nodes, right? So in this case, some node, I mean, for example, like this node, so it is I, D, and I and D, and then in this case, this node can be actually represented as a linear combination of these two, right? So in this case, even though we have 5 different nodes, the third node, is represented already as a linear combination of the previous 2 output nodes. So in this case, it sounds like we have, it doesn't mean anything. I mean, the third node is not useful or not used at all, because that is fully represented as a linear combination of the previous 2, right? So, so that is true actually in the case of I mean, in case we design our neural net as all the linear layers. So if this guy is a linear, and then, I mean, basically we apply the nonlinear units on each different output node, right? And so that creates the difference. That causes the differences. But suppose we just stack another linear layer without any nonlinear layers, any nonlinear units, and then suppose we obtain the output by just connecting all the 5 nodes like this, and then you will have the same effect of just using only the 3 nodes in the intermediate or hidden layer. Okay, so in this case, the final output, which is still be represented as linear and followed by linear, in that case, we don't actually need the third and the fifth one. Okay, but so the nonlinear units are applied for each of these different nonlinear, different linear combinations. Okay, so for example, like y1 equals x1, 2x2, 4x3, and suppose that is the first node, and y2 is 2x1, 4x2 plus 6x3. So certainly y2 is linearly dependent of y1, right? And so up to the linear layers, it has no effect. But once we apply the nonlinear units, such as maybe sigmoid, and then it has a different attenuation factor, right? So the increase, because this guy is 2y1, so given the same x1, x2, and x3, y2 will have a larger magnitude than the y1, right? So once applying sigmoid, and then this y2 will be much saturated much more quickly than the first one, right? So applying those nonlinear units actually creates those two linear combinations work differently in the subsequent layers. 질문이 답이 됐나요? Any other questions? Okay, and then now next let me discuss probably and hopefully one last thing about this Gaussian elimination. And this thing that I will discuss will be quite useful in the later lectures. Okay, so so I want to discuss about representing each Gaussian elimination step as a matrix multiplication. Okay, so can we represent the matrix Gaussian elimination such as row interchanges and the scaling and the row replacement as the matrix multiplication of the original matrix? So for example, so 2, 1, 3, 1, 3, 4, and 2, 4, 6. We suppose we change this matrix into that form of 2, 1, 3, and so on, right? So can we represent this as matrix multiplication? In other words, suppose this matrix as an X, which is our input matrix, and suppose this as Y as our output matrix. And can we obtain Wx equals Y? Yeah, of course we can think of like X times W equals Y, but this is a row-wise operation, so the row-wise operation is should be multiplied on the left. But you can ignore this part. But let me just without no specific reason, let me just give you this equation where X and Y are the input and output of one step of a Gaussian elimination, whether it's a row interchanges or scaling or the row replacement. And then for each particular row operation, can we obtain or represent that row operation as W, where W times X equals Y? Okay, so let me just make it abstract. So suppose we have three columns. I don't even give you number or even the number of columns. So we only know that we have the matrix that has 3 rows. And then what about the row interchanges between the first and the third row? Can we represent that operation as matrix multiplication? So first of all, let's just think of the size of this matrix when multiplied on the left. So after doing the row operation, the row interchanges in this particular case, the matrix size should be the same, right? So in this case, the input and output matrix are of course, stay the same, right? So it is 3 by something, and it should also be 3 by something, right? And then what about this matrix? So it should be 3, right? Because this number should match with this guy. And also the number of rows of W. So this is our W. Okay. So that should be 3, so that we make the matrix size as the same one, right? Okay, and then now let's fill out this 3 by 3 matrix. Okay, and then now we apply the matrix multiplication perspective as a row combination. Okay, so in this case, let's think of these 3 numbers first for the first row in the matrix W, X equals Y, and so you guys know that this guy will work as the linear combination coefficient corresponding to these 3 rows on the right matrix, right? And then we linearly combine these 3 rows, and that will produce the first row, right? And so if it is like 1, 2, 3, and then we just multiply it by 1 and 2 and 3, and then we just add together to produce a single row vector, right? Okay, and once you understand this, and then 4, 5, 6, and then you guys can easily understand that this guy is applied 4, 5, 6, and then that will produce the second row, right? So this is the row combination perspective of a matrix multiplication. Okay, so in this case, so let's just figure out these 3 numbers, and what should be those numbers. So those numbers should be, in case we switch it, interchange it between the first and the second column, the third column, and the third column should be placed as the first column, right? And then what will be the corresponding linear combination coefficient? 0, 0, 1, 0 and 0 and 1, right? Okay, and then what about the second row? Second row didn't change at all, right? So it means, we just apply the linear combination as 0, 1, 0, right? 0, 1, 0, and 0. So in this case, 1, 1, 1, 0, 0, right? So this is a row interchanges, right? So let's extend or generalize it into really larger matrix. So we have many different rows of our original matrix, and then so it's a m by n matrix, and then it is a m by m matrix, and then suppose we change maybe i's and j's rows in this case, and then how can we represent this matrix? We can easily start with identity matrix. Okay, so this identity matrix means from the row combination perspective, the first row of having the coefficient as a 1 and all 0, so that is selecting or picking up the first row and then we place it as the first row, right? So we can understand this identity matrix multiplication on the left row-wise, right? So that produces, that provides the linear combination coefficient for each row. Okay, and then once if we want to change i's and j's row, and then so instead of using dot dot dot, and then I'm gonna just think of the 5 by 5 matrix, and then maybe 2 and 5 row interchanges, and then we pick up the second one, and then we can think of these 4 elements. What are these elements? So these elements are 0, right? On the off diagonal part. And then we pick up those 4 values, and then bringing it into separate smaller matrix, and then it will be 1 0 0 1, which is our identity matrix. And then we just do the row interchanges, and then 1 0 0 1 and 1 0, right? So this guy is placed over here, and this guy is placed over here, and 1 0. Okay. So so it is easy, right? So this is the second set of linear combination coefficient that will produce the second row, right? But instead of setting 1 in the second entry, but we set it as a 5th entry. So then we just bring the 5th row into the second row. Okay. So this is the row interchange operation. And so this is a kind of a generalization into larger matrix where we just interchange between i's and j's row, and we now further extend or generalize this into something called permutation matrix. So this permutation matrix is defined as this P times X, where X is our input matrix, and that is just a general rectangular matrix, and the P is our square matrix. Okay, square matrix, and that square matrix. In the case of permutation, how about so we think of this, the process of shuffling or reordering our rows. Okay, so suppose X has 5 different rows, and then let's just reordering of these rows as maybe 1, 5, 3, 2, 4. So that means previously the first row is becoming the first row, but the second row is actually the 5th row from the previous matrix, and the 3rd row is remain the same, and then the 4th row is actually the second row of the input matrix, and the last row is this guy. Okay, so for this permutation, how can we represent it as this matrix P as a matrix multiplication on the left of the original matrix? Okay, so we can easily understand or construct this matrix. So P should be, first of all, a 5 by 5 matrix, right? Okay, so so we basically think of the row wise, right? And so we have to pick up the first row, and so it should be 1 0 0 0 0, right? And then what about the second row? and that should pick up the fifth row, right? So it's this guy. Oops. Uh-oh. So does it make sense? So this is called the permutation matrix. Okay, and so this is a generalization of just interchanges between only the two rows. Okay. Okay, and then now we still have to think of two other types of row operation used in the Gaussian elimination, and then we dealt with the interchanges, and then how about the scaling of a single row? Okay. So yep. So we have maybe 5 different rows, and then suppose we want to scale this guy by 2. Okay. So we still apply the row combination. Okay. So so in that case 1 0 0 0, right? And then what about the second one? Second row will be 0 2 0 0 0, right? So we still bring the second row into the second row, but we apply the scalar multiple of the factor of 2, right? So that is a row-wise scaling. And then we can also generalize it, right? So we want to scale each row by different factor. So for example, like 1, maybe 4, and -1, and maybe 0. Okay. Yeah. So we want to do row-wise scaling. Okay. In that case, how can we represent that operation with matrix multiplication? Okay. Then matrix multiplication will be still diagonal matrix, and then that diagonal elements will be those scaling factor, right? And all the off diagonal parts will be 0, right? So this is the row-wise scaling. And then also, in the previous case and this one, we applied just a row combination perspective, right? But also we can do this columnized in a columnized manner. So how about interchanging between columns, or do the columnized scaling? Okay. So in that case, we can do the same thing, but we just multiply our matrix on the right. Okay. So suppose we have those 5 different columns, and then maybe scale each column as 1, maybe 3, -2, 1, and 4. And then once we obtain, given this matrix, we just consider the matrix on the right, and this matrix will be 5 by 5 square matrix, and then it's 1 3 2 2 1 4. Yeah, so those diagonal matrices will do the column-wise scale, right? But what about the row column-wise interchanges? Yeah, even though we only do the row-wise operation within the Gaussian elimination, but in general cases where we want to just shuffle or reorder the columns, or scale, apply the scaling row column-wise, and then this matrix will be so in this case, each column will provide the linear combination coefficient, right? So when multiplying the matrix on the right, then right matrix will provide, each column of the right matrix will provide the linear combination coefficient, right? And so so 0, 0, 0, 0, and then this 1 will be multiplied over here, and 0, and 0, and so on, right? So that's how we do the column linear combination of the columns on the left. Okay, then yeah, so if we want to just change the second and the fifth column, and then the first column should be set as 1, 0, 0, 0, 0 to pick up the first column. And then what about the second column? In order to produce the second column, we have to pick up the fifth column. So it will be 0, 0, 0, 0, 1. And 0, 0, 3, 0, 1, 0, 0. And 0, 0, 0, 1, 0. And 0, 1, 0, 0, 0. So does it make sense, right? So in order to produce the second column, we picked up the last column. In order to produce the last column in the resulting matrix, we picked up the second column, right? Any questions so far? 여기까지 다 이해가죠? 하여튼 저런 것들을 좀 잘하고 뭐 그래야 좀 딥러닝이든 뭐 이런 거 다 벡터라이즈드 된 어떤 형태들을 이게 로우와이즈 혹은 컬럼와이즈로 이렇게 좀 바라보는 것들을 지금 연습을 하고 있다고 생각을 하면 될 것 같고. 네. Okay, so far so good, right? And then now let's think of the most difficult operation among the three in the Gaussian elimination, which is the row replacement. Okay, row replacement. So let's see. I'm not sure how much it will bring, but I brought a lot. Okay. Okay, so so in this case, let's think of the row replacement operation, which produces like this. Right, so this was one-step Gaussian elimination result, right? And then how can we represent this as also the matrix multiplication on the left? Okay, let's imagine those W. So what about the first row of W? The first row was is 2 and 3. So the first one was 2 and 3, and that was only used as an eraser, but the first column itself didn't change at all, right? So the first row remains the same, right? And so when imagining the matrix W multiplied on the left of the X, and then what about the linear combination coefficient? It will be 1, 0, 0, right? So it's not changed at all. But what about the second one? Okay, this second row is represented as let's just construct the linear combination of the rows of an input matrix. The second one, so this guy is the first one and this guy is the second. Okay, so those are the names of the rows. Okay, so it is like the original second row, negative or minus the first row times what? 1/2, right? So that is the coefficient that we used in order to make this value as 0, right? So in terms of the row combination, the new second row is represented as this, right? And so what is the second row? What is the second row in the W? So negative 1/2 and 1 and 0. And the third row is 1 and 0. And what is the value over here? Oops. Should have been 3. Right? Where is this number? Minus 1. Right? Okay. Yeah, because we multiplied the first row by 1 and then subtract it from the third row. And so this is our W. So this W can be can be constructed to represent this row replacement. Okay. And let me ask also about the question. Yeah, let me ask the question related to this representation. I mean, so so far what we discussed is that for each row operation, each step in our row operation can be always represented as the matrix multiplication on the left, right? And then let's imagine the sequence of row operations. So for example, so in this previous case, yeah, we did a row replacement that changes the second and the third row, and then we moved onto this guy, right? And then we removed that 3, right? And so we can think of the second row operation step, right? Or row replacement that makes that 3 as 0, right? And then that is the second row operation that we applied, and that also be represented as a matrix multiplication, right? And then the whole sequence of each step of those steps that we applied in the row operation can now be represented as this. Given the matrix X, the first row operation, let's call it as W1, and the second row operation, W2, W3, and so on. So this whole sequence of row operation can be represented as a matrix multiplication on the left, and the further left, and the further left, and so on, right? Now this matrix, okay, this matrix is our final matrix called E, which is a reduced echelon form for that represents, like this matrix. So this is our final result after finishing up the row operation, right? That resulting matrix will be the same as this equation. I mean, that will be our resulting matrix. Okay. And here, let me ask the question of whether each row operation, which is represented as this matrix multiplication, I mean, each row operation, is that invertible or not? So the question is, we can always construct the square matrix that is representing a particular row operation, and for any given row operation, we can represent it as a matrix, and then that matrix W, I mean each W, is it always invertible or not? So the answer is yes. So each row operation is always invertible, and the further conclusion is that this whole part is invertible because each of them is invertible. So let's just think of the inverse matrix. So inverse matrix, I mean, so we can always think of the matrix as some matrix that performs some transformation of a given vector or matrix. So suppose we just applied one step of a Gaussian elimination and produced Y, And then can we obtain another matrix, maybe V, okay, that will produce the original matrix Y, which means we changed X into Y by multiplying W, and let's just ignore this part. And then we just further multiply this Y with the matrix V, which is our new matrix, and then that will produce the original matrix X, okay? And then in this case, X and W and V will be X, right? And so for whatever given matrix X, if we have to satisfy this, and then this V times W should be identity matrix, which has no effect even when multiplied with the input matrix. Okay. So again, this V times W, I mean, if V exists, okay, if V exists, that satisfies V times Y converts back to the original matrix X, okay, and then let's think of V times W as a single matrix, okay, this is a single matrix that transforms our matrix X into just the same matrix X, okay, and then this should be always true for any matrix X, right, because doing the row operation should be should produce the consistently generate the result of this row interchanges or scalings and so on, right? So it is rather it is not rather than being an equation, it is like 항등식 영어로 보죠. So that is the equation that should always true for any given X, right? So to satisfy that requirement, the only possible solution for this V times W as a whole, that should be identity matrix. Okay. So our initially W was a square matrix, right? And for the square matrix, if we can find some matrix V that will produce the identity matrix, and then this V is the inverse matrix W. Okay. So here, although you may view it as a simple, but there are two different perspectives in the linear algebra. So one being just looking at the matrix as it is, and then considering its inverse matrix as it is as well. But let's think of that matrix as a kind of a transformer that transforms an input matrix. Okay, so we can just think of the matrix W as it is, but we can view it as the transforming matrix of the input matrix or vector X. Okay, and then once we found it's an inverse matrix, W inverse, and then what does that mean in the context of this transformation? And that transformation is W inverse and W, and X should remain the same X. Okay, so that means it's like pictorially, so we have a X, and then it will be mapped into some other matrix or vector. Okay, and then so given W, we can always send any vector X into any Y value or Y vector or matrix. Okay, but for any given X, we should always be able to go back to the original X by just applying W inverse to Y. Okay. So that way, the inverse matrix, when viewing it as a kind of linear transforming matrix applied to another kind of input matrix or vector, and then the original matrix will send or map the input into output. But for any given input, if we can find another matrix W inverse, okay, that can always send the output back into the original input. Okay, so once we can find that W inverse, and then so that is the definition or the characteristic of the inverse matrix. So so in this kind of mapping or transformation perspective, okay, so this inverse mapping is the same as having the inverse matrix. Okay, so in that case, so we can also apply the notion, various different notions of the functions or mapping. So first of all, if this function or mapping is invariable, okay, and then what is the necessary condition? What should be at least guaranteed? Yeah, among like, I'm trying to discuss about like, one-to-one or onto kind of mapping property. So let's just think of this really simple function of 1, 2, 3, 4, 5. In this case, let's imagine the mapping of this. So this is a one example of function, right? And then what is not a function? In what cases the function property is violated? So in this case, so this is not an example. This is not a function, right? So function has the two requirements, which is that each input in our domain, or 이걸 정의역이라고 하죠. 정의역이 도메인. Each input or each element in our domain should be mapped into single output. So in that case, one is mapped into multiple outputs. So it violates the first condition of being function. And also for this second one, for this guy, so it has no mapping output, right? So that also violates the function. So at each input, we have to have a unique output, but that unique output can be overlapping with no problem, right? So in the previous case, so 1, 2, and 3 will have one single output, but 1 and 2 will have the same output, so that is okay. So this is a valid function, but when thinking of the inverse function of it, so inverse function cannot exist in this case. And how? So this 4 should be mapped into multiple ones, right? So that way, the output should be mapped from unique input. Okay, so that is called what? One-to-one mapping. Right? So this is the requirement. One-to-one mapping is the requirement. Is required to obtain or for the inverse mapping to exist, right? Okay, so back to this linear algebra case. So now we can think of the input as a matrix or vector, but let's just simplify it as a vector. So if our W is a 3 by 3, and then what is the input domain? It is 3-dimensional vector, and also the output is 3-dimensional vector. So it is like 3 by 3 and input vector x, right? So this is W and x, right? So in this case, how can we achieve the one-to-one mapping? When when can we not achieve the one-to-one mapping? So one-to-one mapping cannot be achieved when we have linearly dependent columns. So why? So So we have like 3 different columns in our W, and W times X is always understood as a linear combination of the 3 columns, right? And then so let's think of these 2 columns, and then the linear combination output was mapped into this, right? And then it is like so if we apply the parallelogram rule, and then we will have a corresponding scaling factor of the first basis vector and the second basis vector to produce the resulting vertex in our parallelogram, right? So that is our function output. So that is one point in our codomain, or in 공역에 있는 혹은 치역에 있는 한 점이죠. Okay, and then now what if we have linearly dependent vectors? So the third vector is linearly dependent of the previous 2. In that case, producing the same outputs, we can now have a multiple different ways. So by using these 2, we can form the parallelogram. So we have like 3 different vectors that are linearly independent, having inside of the same plane, and then we want to produce this output vector, and then this output vector can be formed by this parallelogram, but also formed by this parallelogram, right? So that means we have a multiple possible choices of a linear combination coefficient that will produce the same output, right? And so it means exactly the same as this situation. So even though in this case our domain and the codomain is R, but you can now think of each element as a 3-dimensional vector, okay, which work as a linear combination coefficient. So now 2 different linear combination coefficients will be mapped into the same output vector. Okay, so in that case, can we come up with or obtain the inverse mapping? It is not, because it is not a one-to-one, right? So that way, linearly, if we have a linearly dependent column, and then this many-to-one mapping exists, and thus in that case we cannot consider, or we cannot obtain the inverse mapping. Okay, and thus just back to this purely looking at that matrix itself. So if that W has a linearly dependent column, and then W has no inverse matrix. Okay, so let me just quickly describe how to compute the inverse matrix of each elementary operation, or each row operation. So in the case of row scaling, so for example 1, 0, 0 and 0, 2, 0 and 0, 0, 3, for example. So in this case, we are scaling the first row by 1 and the second row by 2, and when having this matrix multiplication on the left, and then this is the row-wise scaling, okay? And then now, let's imagine another matrix that is further multiplied on the left that will produce the original matrix. And then what will be this matrix? It will be 1, 0, 0 and 0. And why? So we want to recover the original matrix, and through this transformation of row-wise scaling, we scaled each row by 1, 2, and 3, right? And then how can we recover it into original matrix? And then we still do the row scaling, right? The first row was scaled by 1, and thus we scaled it again as 1. But the second row was scaled by 2, and thus in order to recover the original one, and then we can just apply the scaling factor of 1 over 2, right, for the third column, and then we can apply the 1 over 3, right? So this is inverse matrix of W, right? From the transformation perspective. And once you can just compute the matrix multiplication with this guy and that guy, you can easily verify that is producing the identity matrix. Okay. And then what about the row interchanges? So yeah, maybe 2 and 5 shifting 1 0 0 0 0 0 0 0 0 1. Okay, I'm gonna skip writing the rest of the part. So in that case, how can we recover the original matrix? What will be the inverse matrix of that operation? We interchange it between the second and the fifth row, and then how can we recover the original matrix? I mean, we can apply the exact same operations once again, right? So we change it second and the fifth, and then we again change the second and fifth, and then it will become the original matrix, right? So interestingly, in this row interchange matrix, what is this inverse matrix? The inverse matrix is the same as the original matrix. Okay. So this guy is, suppose that is called P. I mean that P is the acronym for permutation. So permutation is, I mean, the row interchanging. I mean, permutation is like shuffling or reordering the rows like this. So this is a permutation matrix, but this row interchanging is, I mean, only a pair, interchanging of only a pair of rows is a special case of this permutation matrix, right? And then if we consider this a row interchange matrix and then call it as P, and then P times P will be what? It will be identity matrix, right? So interestingly, this guy has the inverse matrix as the same as the original matrix. And yeah, in general, this kind of property or this kind of matrix has the special name. If I remember correctly, it is called. Does anyone know about the name? It is, yeah, it is just a mathematical term, but idempotent. Yeah. Let me see. Yeah, so idem is like an identity matrix, and I don't know about the meaning of the potent, but oh, it is a I'm actually wrong. Yeah, so idempotent property is defined as when multiplying the matrix 2 times, and then it will be the same as the same matrix. Yeah, so right. But yeah, so that idempotent is actually coming up when considering the projection matrix. So for example, yeah, so let me finish it by just let me just add one more thing. So suppose we just do the orthogonal projection of a point onto the line. So for example, so we have a point over here, and then we have a line over here, and then its orthogonal projection will be this point, right? So this is called the projection, and the projection, the projected plate space is sometimes line, or it can be plane, right? So if we have a one vector, and then we can always project it on orthogonally to that plane, right? So in the case of this orthogonal projections, and then this projection is represented as a matrix multiplication. Okay, so suppose that matrix is W and the given vector X. So suppose this guy has the effect, or that actually maps the point into this, projected point. And then what if we just do this projection twice? So after doing projection once, and then this point has moved to here, right? And then projecting that point, which is already onto the projected plane, projecting it once again, and then that will not change at all, right? So projecting it once or twice will be the same. So W times W is remaining just W, or even like W to the power of 3 or 4 is the same as just a single W, right? So that is called idempotent, and the representative example of satisfying this idempotent property is this projection operation for matrix. Okay, so time's up. So yeah, and yeah, I'll do some poll, but yeah, I got some call maybe on half of it, and I may have so there is possibility that I may not be available this Friday afternoon. So likely the only option will be sometime on the next week's Friday afternoon. But I'll confirm with my other schedule, and then post some doodle, and then send an announcement. Okay, thank you very much. 네, 일단 지금 정확한 시간 정해지지 않습니다.
여기 그러면 1시간 반을
그게요. 우리가 추석이랑 대천절이 있어서 너무 많아서 이렇게 보강을 하게.
보강은
일단은 가수결에 있어 이렇게 하기로 했고, 그다음에는 뭐 혹시 못 오게 되더라도 강의를 녹화를 해갖고
그래서 민영이가
그러면 시간은 다시 투표를 하게 돼요.
근데 오니까 뭐
너무 대놓고
크게 뭐 차이가 많이 있을 수는 없겠죠. 다음 주 금요일 아마도 이번 주가 힘들 것 같은데 다음 주 금요일이 중에. 밤이요? 아까 그 밤이랑 금요일날 밤? 금요일날 밤?
사실 나야 손가락에 병
그거까지 해갖고요. 내가 투표를 한번 해볼게요.
나는 그러면은
그거요. 그게요. 그 얘기 안 하는데 그냥 이게 내가 지금 뭐 이런저런 거의 뭐 마음 가는 대로 제가 진도를 나가고 있긴 한데 일단은 우리가 이렇게 하고자 하는 그 머티리얼이 있긴 있어요. 뭐 강의 자료나 이런 것들이 있긴 한데 혹시 이제 그거의 비중을 좀 줄이고 뭐 이렇게 저기 리니어 알gebra 관련한 내용이 어디 뭐 머신러닝이나 이런 쪽에서 나온 논문에 뭐가 있어서 좀 이 부분이 이해하기가 어려운 부분을 좀 집어서 뭔가 좀 공부를 하자라고 하면 그런 거를 좀 신청을 받겠다. 좀 전달이 제대로 안 된 거 같네요.
근데 그냥
했어요.
없는 건데.
네?
없는.
아까 내가 여기 올려달라고 했는데 없는 것 같아요 아직은. 근데 뭐 그러니까 앞으로 그러니까 뭐 오늘까지만 신청 받는 건 아니고.
그냥 일단 계속
네네.
보내면.
네네 맞아요. 네. 네네.
질문이 하나 있는데요. 마지막에 그 적등행률 설명하실 때
응?
이거 아이덴
네네.
네. 아이덴포텐트
네.
이게 최고에는 몇 등행률이더라고요.
몇
등.
등.
네,
네.
한국어로 하면.
네네.
이거 A 곱하기 A는 A인 어떤 행률 A를 말하는 거죠, 이게.
네.
근데 그거 마지막에 그림 그려주시면서 여기서 뭐 수학적인 설명해 주신 것 같은데 그 부분을 좀 놓쳤거든요.
네. 그러니까 이게 그 프로젝션이라고 하는 어떤 오퍼레이션 혹은 매핑이 있는데
네.
그것도 이제 뭐 아직 우리가 엄밀하게 배우진 않았지만 그것도 어떤 매트릭스 멀티플리케이션으로 표현이 될 수가 있어요. 네.
네.
그러니까 우리가 이렇게 올소건널하게 수직으로 쭉 이렇게 사용을 시킨다는 게
네.
실제로 그 주어진 어떤 인풋 벡터에다가 어떤 매트릭스를 곱하는 형태로 그 어떤 값을 아웃풋을 구할 수가 있거든요.
네.
근데 이제 중요한 게 만약에 프로젝션을 2번을 한다. 그러면 여기서 일로 이미 왔고
네.
이걸 가지고 또 프로젝션을 하면 자기 자신의 머물러 있을 거잖아요.
네.
그러면 이거를 한 번 프로젝션을 하는 거는 W를 한 번 곱하는 거.
네.
두 번째 프로젝션을 또 한다? 그럼 W 또 곱하는 거잖아요.
네.
W 곱하기 X가 결국은 한 번만 한 WX랑 똑같은 거잖아요.
네.
그러니까 이제 W 곱하기 W가 W랑 똑같으죠.
아 그런 의미에서.
네, 그래서 이제 프로젝션이라는 어떤 오퍼레이션은 그 아이덴포텐트의 대표적인 예다라는 거죠.
알겠습니다. 감사합니다.
네.